Hi everyone, thanks for joining me today for this session, which is about advanced serverless messaging patterns for your applications. My name is Talia Nasi, and I'm a senior developer advocate for AWS Serverless. And so my job is just to build serverless things and then teach the world about them. Before becoming a developer advocate, I was a test engineer for a few years, and I worked at companies like Visa, Forbes, WeWork, Meetup. You probably know me as the girl who tests in production. I also have my Twitter handle here in case you want to contact me or follow me just for more fun stuff. So why are we here today? Why did you all decide to come to my wonderful tech talk? This is a 300 level talk, and we have about 45 minutes today. We are going to start with a quick review of serverless and messaging, and then we're going to get into the different serverless messaging services, say that 10 times fast, and then what the differences are between them. Then we're going to discuss dead letter queues, and then we'll get into combining messaging patterns. So let's get started. So what do we mean when we say serverless? When we say serverless, we mean it's the removal of server operations. And this is an important distinction for customers because it allows you all to focus on the building of the application rather than the management and scaling of the infrastructure that's needed to support the application. And these are the four tenets that define serverless as an operational model. So firstly, there's no infrastructure to provision or manage. There's no servers to spin up, operate, or patch. There's no physical or virtual container orchestration. Serverless applications automatically scale by unit of consumption rather than by server unit. And this is important for companies because generally you create multiple MVPs and you don't want to build all of them out for scalability because you don't know which ones are going to last in production. You don't know what's going to make it. And so this is really great for that. Serverless has a pay-for-value billing model, which means you only pay for what you use, not for idle time. So if you have an idea that's not taking off, sometimes they can get expensive. So this means that you can experiment more. So let's say I have an idea for a new feature, and Bob has a competing idea for a new feature. Bob and I can run an A/B test, and we can A/B test our features. Regardless of who wins, regardless of which feature wins, regardless of which one has a higher conversion rate, it's not going to cost much because you only pay for what your customers are using. And lastly, serverless applications have built-in availability and fault tolerance, so there's no need to architect for availability because it's built into the service. And this is important because things will break, like unexpected things happen. Data centers have outages, there's earthquakes, and spaghetti and meatballs can fly from the sky. So what do you do if the servers handling your project fall over? How do you know that all of your versions are in sync with all of the regions? Have no fear, serverless is here, my friends. This all happens automatically. And just to note on security, you don't have to build your own, right? So whether you use Cognito or a third-party solution like Auth0, these are enterprise-grade services that help you implement security. And with serverless, you can precisely define how different services and resources can interact. IAM also gives you granularity to ensure that in a well-architected solution, your application can have a strong security posture. Now, at the center of serverless is, drumroll please, AWS Lambda, right? This is a serverless product that's at the core of a few terms: event-driven computing, functions as a service, and it's serverless, which means it meets our four qualifiers that we just talked about. AWS Lambda lets you run code without provisioning or managing servers. You only pay for the compute time you consume, and there's no charge when your code is not running, so you're not paying for idle time. With Lambda, you can run code for virtually any type of application or backend service, all with zero administration. All you have to do is upload your code, and then Lambda takes care of everything required to run and scale your code with high availability. You can also set up your code to automatically trigger from other AWS services or call it directly from any web or mobile app. But Lambda doesn't just sit in a vacuum by itself. It's one of the parts of a serverless application. It's one of the components. And typically with Lambda functions, there's an event source or trigger, and then there's the destination. And so the source has a number of services that can directly interact with Lambda, and we're going to talk about some of these today. And these events can be almost anything. So they can be an HTTP call, they can be a cron job, they can be something uploaded to an S3 bucket, they can be changes in a resource state, it can be something from a third party, so a payment arriving through Stripe. So the event is something that happens that causes the Lambda function to come to life. You then have the Lambda function, which provides curated execution environments with all these different languages built into it. And we have a runtime API, so you can basically bring any language you want into Lambda. Then you have the destination, and that can be whatever your code needs to interface with. So this is entirely up to you. It depends on your business logic and your requirements. So an example of this flow would be a customer pays for something, the payment gets processed, and now they can get access to the service. And when it comes to thinking about how Lambda works, I just want to stress this again. We're going to be focused on both event sources for a Lambda function. So these are the things that you can use to trigger your Lambda function, and what the differences are and how you can use them and choose between them. But also remember, Lambda can interact with other downstream services, some of which are also possible event sources. So bear in mind during this talk how the various services work, so you can also choose the right destination based on what your function needs to do next. So this talk is going to be focused on advanced serverless messaging patterns. And before we get into the architecture, let's take a second to understand what we mean by messaging and how this interacts with our serverless compute platform, AWS Lambda. So most serverless application architectures use a combination of different services. And this can be different AWS services, microservices, Lambda functions, things like that. And so messaging services are important in allowing distributed applications to communicate with each other. And these are fundamental to most production serverless workloads. And so what do we mean when we say messaging? Messaging services enable different software systems and end devices to communicate with each other. And what's great here is that the communication can be in different programming languages, it can be in different platforms, it doesn't matter. And you can use messaging services to send and receive data in your cloud apps. So the messaging services we'll talk about today are serverless, which means they meet our 4 tenets previously discussed. And the underlying infrastructure is automatically provisioned for high availability and message durability to support the reliability of your applications. Messaging services can improve the resilience, availability, and scalability of applications when used appropriately. They can also enable your applications to communicate beyond your workload or even the AWS cloud and provide extensibility for future service features and versions. Messaging is great for resilience because SQS, for example, is Amazon's serverless queuing service, which we'll talk about in a little bit. If your service fails to take a message off of the queue, SQS retains your messages and you don't have to worry about losing information and losing data. Messaging also provides high availability. So if there's a service disruption, if something goes down, if something unexpected happens, these services run in multiple availability zones, in addition to the fact that if your consuming systems have issues, SQS can help you. Message queues also improve scalability by enabling you to decouple different parts of your application and then scale them independently. So let's talk about scale for a minute. And a great example of using messaging to scale is the Amazon.com site. So the main objective of this site is to get you to click on the place order button, right? And once you press that button, a bunch of things happen. First, we check your credit card to make sure you can pay. And then we have to get the merchandise off the shelves, get them onto the trucks, and so on. And all of that happens in an Amazon warehouse, right? There's no synchronous API call for the Amazon backend to ship and package your products, right? What the front end does after your payment is confirmed is that it puts together some information describing the event and what happened, and it puts your account number, your credit card info, everything that you bought, all of that information goes into a packaged event, and that gets put into the cloud. And then later, another piece of software is going to pull that off and start the packing, the shipping, and the delivering, and all of that. The key point about this process is that these things can all happen at different rates. So normally, the rate at which people click place order and the rate at which the warehouses can get the boxes out of the doors are roughly equivalent. But on days like Prime Day, Black Friday, just really big sale days, people hit that button much, much faster than the warehouses can operate. And that's okay, because these order events are going to be added to the queue and will be picked off from the cloud as the backend services work through them. So with Lambda, we have a number of different execution models that we support. There's the synchronous push-based model, and in this case with API Gateway, where it calls the order API, this then invokes a Lambda function, which may then interact with another service, and then synchronously can send back the response to the client. So in a synchronous model, the client waits for the response back from the service before proceeding. Then there's an asynchronous or event-based model, which we just saw, where services such as SNS or S3 might invoke a Lambda function based on a message being put into a topic with SNS or an object being put into an S3 bucket. Now, the asynchronous functionality of Lambda returns that it has received the event and then carries on processing without the service that invoked the Lambda function waiting for the response. And then lastly, there's the stream or pull-based execution model. In this case, with examples such as Amazon Kinesis and Amazon DynamoDB, these services are going to send out a stream of changes. And so the Lambda service will actually pull for and pull down these changes or those records and then invoke a Lambda function on your behalf. So 3 main execution models: synchronous, asynchronous, and stream-based. And across these live a number of different services that can invoke Lambda functions. And the ones we're going to focus on today are Amazon SNS, which is our simple notification service, Amazon SQS, our simple queue service, and then our handy-dandy event bus service, Amazon EventBridge. So these are the 3 most useful messaging patterns for serverless developers. They deal with queuing, publish, subscribe, and event buses. And these are provided by the 3 services that we just mentioned: SQS, SNS, and EventBridge. And all of these services are serverless, which means, again, they meet our 4 tenets. So no infrastructure to manage, automatic scaling, pay only for what you use, and it's fully managed and highly available. All 3 of these services integrate with Lambda, which allows you to publish messages via the AWS SDK and invoke functions as targets. Each of these services has an important role to play in serverless architectures. SQS provides queues for your serverless application, similar to the one we just saw from Amazon.com. You can use a queue to send, store, and receive messages between different services in your workload. Queues are an important mechanism for providing fault tolerance in distributed systems and can help you decouple different parts of your application. SQS scales elastically, and lucky for you, there's no limit to the number of messages per queue. The service durably persists messages until they're processed by a downstream consumer. With Amazon SNS, you can send messages reliably between different parts of your infrastructure, like send confirmation emails after someone buys something from your e-commerce site. It uses a robust retry mechanism for when downstream targets are unavailable, And when the delivery policy is exhausted, it can optionally send those messages to a dead letter queue for further processing. And we'll talk about dead letter queues in a second. SNS uses topics to logically separate messages into channels, and then your Lambda functions will interact with those topics. Amazon EventBridge is a serverless event bus service which simplifies routing events between AWS services, SaaS providers, and your own applications. It logically separates routing using event buses, and then you can implement the routing logic using rules. You can filter and transform incoming messages at the service level, and then route events to multiple targets, including Lambda functions. Also, a service we won't get into much detail today is Amazon Kinesis. So Kinesis is great for real-time stream processing, and this allows you to ingest a lot of data at a time, and it's highly scalable. You would use this for real-time ingestion of, say, click data for your website, or sensor data from the tractors in a field, or streaming lots of log data somewhere. So Lambda can read the stream, analyze it, and then modify the data en route, do some analytics, and then send it somewhere else. Okay, so let's talk about SNS and Lambda. So Amazon SNS is one of the oldest services that we have here at AWS. It's used very heavily by customers of AWS, both enterprise level and startup level. SNS is a simple, flexible, fully managed pub/sub messaging and mobile push notification service for high throughput and highly reliable message delivery. So essentially what this means is that you can publish messages into what's called an SNS topic, and then that SNS topic has the ability to then push or deliver those messages out to the services that have subscribed to that topic. The publish is an asynchronous process, so once SNS has received the message, the publisher can carry on, confident that SNS will handle the message reliably. These can be HTTP or HTTPS endpoints, mobile devices, SQS queues, or in the case of what we're talking about today, Lambda. So as messages are put into an SNS topic, the SNS service can then go in and directly invoke a Lambda function with these messages, and then your Lambda function can consume that message, that record, or that data, and then execute it. And then there's a few interesting things that SNS can do. So one is it has the ability to have multiple subscribers to a given topic. So let's assume that you have a complex microservices environment. And let's say you have, for example, a checkout process. You could put a message onto an SNS topic that says that an order was placed and that it should be consumed by all of the things that it needs. So a credit card processing service, a shipping service, an inventory service, a fulfillment service. All of these are subscribed to this SNS topic that would then get the same message and then act upon it independently from each other. But then again, all they're doing is processing that same single message. You can then do more sophisticated things on top of this, as well as filter some of those messages. So only certain subscribers get the message, and let's say that at some point somebody cancels an order and you only need to update some of those services, you can set to only filter based on a canceled order. Another service that's integrated very deeply into the AWS platform today is SQS, or Simple Queue Service. SQS is a simple, flexible, fully managed message and queuing service to send, store, and receive messages between software components at any volume without losing messages or requiring other services to be available. It's basically a managed queue service that allows you to publish messages into it. The Lambda service then can pull a queue looking for new messages, and when it finds messages, it's going to grab them and invoke the Lambda function on your behalf. Now, SQS is technically the first web service that Amazon ever launched, and it goes way, way back before actually technically there was AWS as a business side of Amazon. SQS is used very heavily internally at Amazon and AWS and by customers of all shapes and sizes to do massive throughput of queued message delivery. And in regards to SQS and Lambda, it's pretty straightforward. You basically point Lambda at the queue, and what happens is the Lambda service maintains a puller that pulls the messages out for you. And these messages are processed in batches, and basically you're allowing the function to consume those batches, and then you can process the messages in the batch. Now, SQS has two types of queues, the standard queue and the FIFO queue. Standard queues have at least once delivery, so there's the potential for a message in SQS to be consumed by more than one reader. As a large distributed system, it really favors durability and availability of the service, but what can happen potentially is there's a rare chance that a message could be pulled out more than once, and so you just have to think about that and how that would impact things. SQS also now has FIFO queues, so first in, first out, which do strictly guarantee the ordering of messages as well as ensuring that there aren't any duplicates. The trade-off here is that you have fewer transactions per second compared to standard queues. So if we look at the same architectural diagram for EventBridge, we see it's a simple, flexible, fully managed event bus router to connect applications together. So with EventBridge, your events are published to an event bus, and then you set up rules that match something in the event, and then you route the event off to one of 18 services, one of them being Lambda, which can process the event. And the handy dandy thing with EventBridge is you can have multiple event producers adding very different events to a single event bus and simply use rules to filter the different events and route them on. Amazon can also use streams. So Kinesis Streams is a fully managed, highly scalable service for collecting and processing real-time data streams for analytics and machine learning, and really all sorts of use cases. The way it works with Kinesis is that as data is put into a stream, the Lambda service will pull that stream looking for changes and looking for new records to be put in. It's going to put those records out and inject them into a Lambda function via an invocation. And now Kinesis is a really great product that has a lot of different capabilities as well. And it's meant for really massive throughput, ingesting data, potentially terabits per second. So with Kinesis, you create a stream, and then based on throughput, your stream is then split into shards, which have a fixed amount of capacity and throughput. Lambda will then receive batches of messages off to those shards in parallel. Just like how SNS supports the ability of a fan-out model for sending messages to multiple receivers, what Kinesis allows you to do is have multiple consumers off of the same stream, such that you could have individual applications that are pulling in all the same data. Now, in this case, there isn't really a way for you to filter those messages out to, say, prevent one application that's consuming a stream from getting some messages and not others. But this does support the ability for you to do multiple parallel application path workloads for things like near real-time analytics and data processing. I just want to call out something else with microservices. So although we've only been talking about how to connect many microservices together, there's also times where you may need to get more coordination than just set and forget asynchronous messaging between applications. And this is really where AWS Step Functions shines. Step Functions is a serverless workflow automation service, which is tightly integrated with Lambda. You create state machines which have tasks, choices, and branching logic to coordinate the components of a workflow transaction, stitching together services such as Lambda. Another common challenge is handling payload sizes in different services. So consider an application moving a payload from API Gateway to Lambda to Amazon SQS. So API Gateway supports payloads up to 10 megabytes, while Lambda's payload limit is 6 megabytes, and the SQS message size limit is 256 kilobytes. In this example, you could instead store the payload in an Amazon S3 bucket instead of uploading it to API Gateway and then pass a reference token across the other services. The token size is much smaller than any payload limit and may provide a more efficient design for your workload depending on the use case. So there's 6 primary criteria that I think about as a comparison for messaging services. There's definitely other things that we could talk about, like maybe complexity, but these 6 are the biggest things to help people think about which of these services that they should consume. These include scale and concurrency controls, the durability of the data inside one of these services, the persistence of data inside of the services, the consumption model and how to think about how applications take data out of the services, and finally, the failures and retry handling models for each are important to consider for when choosing your workload. So another way to visualize the different concurrency models is this handy dandy visualization we have here. So with SNS, EventBridge, and the Lambda API, it's a 1-to-1 ratio. So each notification, event, or API call is going to trigger a Lambda invocation with the one event. With SNS and EventBridge, it's a best attempt to deliver messages in the order they were received. SQS will also trigger one Lambda function for each event, but events can be batched up in a queue and are not lost. This can be a useful buffer to store events for asynchronous handling, even sometimes later. With standard queues, there's no ordering, but with FIFO queues, there is. And then for stream-based with Kinesis, it's going to store the data in the stream like with SQS, but it's parallelized. So streams are often subdivided into shards to handle increasing throughput, and then each shard sends batches to Lambda, and inside each shard, the messages are ordered, which is useful for when you want to make sure that you're consuming the messages in the order that they were sent. An example of this would be log streaming or click traffic, where the time order is important. Now, what happens if something unexpected happens? If there's a backend error or your Lambda code doesn't work, something just unexpectedly bad happens. How do you make sure that your messages and your data are not lost? What you do is you configure your Lambda function with a dead letter queue to save discarded events for further processing. Dead letter queues, or DLQs, are a common capability in queuing and messaging systems that allow you to handle failures in the event that your messaging receiving systems are failing. They provide a way for failed events or messages to be captured and then sent to another system, which can store them for future processing. With DLQs, you can have greater resiliency and improved recovery from any failure that happens. Dead letter queues are useful because they make sure that you don't lose your event or data in the event that things go boom. For example, with SQS, let's say an event gets added to the queue. A customer places an order on your e-commerce website, and so that event gets sent to SQS. But then, oh no, there's a problem with your Lambda function, and the customer doesn't receive a confirmation email. So in this case, that message is going to be retried and eventually sent to the DLQ. So this allows you to process the message later instead of losing the message. Sometimes EventBridge can fail to deliver an event to a target in certain scenarios. Events that fail to be delivered to a target due to client-side errors are dropped immediately. Examples of this are when EventBridge does not have permission to a target AWS service, or if the target no longer exists. This can happen if the target resource is misconfigured or if it's deleted by the resource owner. For service-side issues, EventBridge retries delivery of events for up to 24 hours. This can happen if the target service is unavailable or the target resource is not provisioned to handle the incoming event traffic and the target service is throttling the requests. EventBridge's DLQs are made possible today with SQS standard queues. With SQS, you get all of the benefits of a fully serverless queuing service. So no servers to manage, automatic scalability, pay for what you consume, and high availability and security built in. You can configure the DLQs for your EventBridge bus and pay nothing until it's used if and when a target experiences an issue. This makes it a great practice to follow and standardize on, and it provides you with a safety net that's active only when it's needed. With dead letter queues and custom retry policies, you have improved handling and control over failure in distributed systems built with EventBridge. And so with DLQs, you can capture failed events and then process them later, potentially saving yourself from data loss. To configure a DLQ for EventBridge, you can use the EventBridge target and the puts API. So you can combine these services to solve specific challenges in distributed architectures, but why would you want to do this? Because when you combine messaging patterns, you can use specific features of each service to build sophisticated patterns with little code. These combinations can make your applications more resilient and scalable and reduce the amount of custom logic and architecture in your workload. So the first pattern we're going to talk about is SNS to SQS. SNS has a robust retry policy that results in up to 100,000 delivery attempts over 23 days. If a downstream service is unavailable, it may be overwhelmed by retries when it comes back online. You can solve this issue by adding an SNS queue. So adding an SNS queue between the SNS topic and its subscriber has two benefits. First, it adds resilience to message delivery since the messages are durably stored in a queue. And second, it throttles the rate of messages to the consumer, helping smooth out traffic bursts caused by the service catching up with missed messages. To build this in an AWS SAM template, you first define the two resources and the SNS subscription. Then you provide permissions to the SNS topic to publish to the queue using the AWS SQS queue policy resource. To test this, you can publish a message to the SNS topic and then inspect the SQS queue length using the AWS CLI. This results in the following output. Another usage of this pattern is when you want to filter messages in architectures using an SQS queue. By placing the SNS topic in front of the queue, you can use the message filtering capabilities of SNS. This ensures that only the messages you need are published to the queue. To use message filtering in AWS SAM, use the AWS SNS subscription resource. Next, we're going to combine the features of both EventBridge and SNS. So both SNS and EventBridge have different characteristics in terms of targets and integrations with broader features. In this pattern, you configure an SNS topic as a target of an EventBridge rule. In the AWS SAM template, you declare the resources in the preceding diagram as follows. The default bus already exists in every AWS account, so there's no need to declare it. For the event bus to publish matching events to the SNS topic, you define permissions using the AWS SNS topic policy resource. EventBridge has a limit of 5 targets per rule. In cases where you must send events to hundreds or thousands of targets, publishing to SNS first and then subscribing to those targets to the topic works around this limit. Both services have different targets, and this pattern allows you to deliver EventBridge events to SMS, HTTP, email, and SNS mobile push. You can transform and filter the message using these services, often without needing an AWS Lambda function. Also, SNS doesn't support input transformation, but you can do this in an EventBridge rule. Message filtering is possible in both services, but EventBridge provides richer content filtering capabilities. Additionally, this pattern allows you to deliver events to Lambda functions in other AWS accounts and in other AWS regions. You can invoke Lambda from SNS topics in other regions and accounts, and it's also possible to make SNS topics publicly read-only, making them extensible endpoints that other third parties can consume from. SNS has comprehensive access control, which you can incorporate into this pattern. The next pattern we're going to talk about is EventBridge to SQS. So EventBridge can route events to targets such as microservices, and in the case of downstream failures, the service retries events for up to 24 hours. And for workloads where you need a longer period of time to store and retry messages, you can deliver the events to an SQS queue in each microservice. This durably stores those events until the downstream service recovers. Additionally, this pattern protects the microservice from large bursts of traffic by throttling the delivery of messages. The resources declared in the AWS SAM template are similar to the previous examples, but it uses the AWS SQS policy resource to grant the appropriate permission to EventBridge, and you can see that here. Okay, so now that you have all of this information and all of you are messaging experts now, what do you do with it? When you're thinking about when to use EventBridge or SNS, these are some of the things to think about. And these are the things that you'll think about when you're architecting the different applications that you're creating. So EventBridge has more AWS event sources built in than SNS, and you can use SaaS integrations. You can have your own software as a service integrations. There's also more targets integrated between a wide variety of services, including step functions. SNS is great for fan out and can support millions of subscribers per topic. EventBridge, on the other hand, only has 5 targets per rule. So you can use a combination of EventBridge and SQS, like we just talked about, if that's something that that your use case is needing. SNS also has many, many more subscribers. It can support millions of subscribers per topic. In terms of filtering with Amazon EventBridge, the rules apply to the entire event body. With SNS, the filters apply only to specific message attributes. So that it also depends on your specific use case and what you're looking for in the event. With EventBridge, it's easy to distribute to other accounts as well. SNS is also great for applications with very high throughput or low latency messages published by other applications. So SNS is really great for fan out. EventBridge's event is using an event bus that lets you talk to other AWS services. So now let's discuss when to use EventBridge versus some other services. So you'll want to use CloudWatch if you're only using AWS services as sources, because it only uses the default event bus and there's no SaaS integrations. When to use SNS or EventBridge. So again, like we just said, for high throughput, millions of subscribers, very low latency, SNS is a great choice because EventBridge only has limited targets and there's no ordering. You can only filter on attributes and you may need multiple topics. For SNS, it's a really great option if you have millions of subscribers, but it's not a good option if you need to filter by the whole event body, because here with SNS, you can only filter by attributes. For Amazon Kinesis, Kinesis is really great for real-time processing at large scale, routing and storing. It also guarantees order, but there's limited consumers per stream, and it's not serverless because it doesn't scale automatically. For SQS, it's great when you need resiliency, and it's great when you need guaranteed ordering. But with EventBridge, you don't have filtering and you don't have ordering. So to summarize, there's many ways to get data between microservices and for you to use the different messaging tools that we have. Kinesis, SNS, SQS, EventBridge, and the Lambda API are just a few of the ways. You might need to create an API yourself. What you should do is compare the scale, durability, persistence, consumption models, retries, and pricing, and you may need more than one in some part of your infrastructure. And those are the complex examples that we went through with our AWS SAM templates. You should evaluate and test using the SAM CLI, and serverless pricing models make testing new ideas low cost and easy to get started with. If you're like me and you can't get enough of serverless, head over to serverlessland.com, where there's more resources, blogs, videos, and workshops. and more learning paths to help you learn more about developing serverless solutions on AWS. Today, we talked about a lot of different serverless messaging patterns, but those are just some of the many, many patterns you can create with serverless services. I wrote this blog post that goes into more detail about getting started with serverless patterns. The Serverless Patterns Collection is both an educational resource to help developers and an aid for developers that are getting started with building serverless applications. When you use these patterns, whether they're messaging patterns or not, you can experience firsthand what's possible in the realm of serverless. And the entire collection is also available in GitHub so that you can clone it locally and build upon it in your organization. And so in this post, I explain the benefits of these patterns, and I walk you through a few examples that you can deploy from your AWS account. Thank you all so much for joining. Again, this is my contact information, so feel free to follow me for more content, and I hope you all have a great rest of your day.